So in the last lecture, I talked about the fact that in the real line, the Cauchy property for sequences is equivalent to convergence, although not generally in arbitrary norm spaces. Convergence is stronger than Cauchy, and so in some norm spaces, it's possible to have Cauchy sequences that don't converge. More generally, Rn is what's called complete in the sense that every Cauchy sequence converges. And again, that rests upon the completeness axiom for the real numbers, the least upper bound property. Now, the norm spaces that are complete are so important that we give them a name. They're called Banach spaces. So a Banach space, I see it right over here, is a complete norm space. And these are among the most fundamental things in functional analysis, Banach spaces. It's important to know when a norm space is complete. Sometimes it's easier in norm spaces to work with series rather than sequences. A series, summation as n goes from 1 to infinity, x of n, in our norm space x, starts with a sequence of terms, x of n, but instead of considering the convergence of that sequence itself, we consider what we call the series, and this is more closely tied to another sequence called the sequence of partial sums. The nth partial sum, let's call it y sub n, is the sum of the first n terms of the series. It's the sum as I goes from 1 to n, x of I. And we say the series converges to, let's call it S, and we'll call the limit of a series the sum rather than the limit sum. And we perversely use the same notation for the sum as for the series itself. Summation as n goes from 1 to infinity, x of n converges if the sequence of partial sums converges to S, if y sub n converges to S. We'll see in a few minutes that we can actually go back and forth between sequences and series. Not only are sequences handled in terms of, series handled in terms of sequences, but vice versa, we can handle sequences in terms of series. First of all, what would the condition that the sequence of partial sums being Cauchy, what would that translate into for the terms of the series x of n? It's not hard to see that the series is Cauchy if for all epsilon greater than 0, there exists an n sub 0 in the natural numbers such that the norm of the sum of the segment as I goes from n to k of x of I is less than epsilon for all n, k, rather greater than or equal to n, greater than or equal to n sub 0. This is the most convenient way of phrasing the Cauchy criterion for series.